Wait, I need to share this.
Recording is on.
Okay. Hi everyone. So this week we are going to discuss these two problems. First one is create queue data structure using linked list, and second one is a like a cloning of a linked list. Okay, let's see what is the how can we create a queue using a linked list. There is a nice Geek for Geeks website here. I'm going to show you. They have a really nice diagram. I no need to draw again. So here is the queue, right? Stop me anytime and unmute anytime, no problem. So we can, it's all discussions. It's not like any big session. It's just a discussion session. Anybody feel free to, stop me and start sharing your thoughts. Okay. So here is the queue works, right? Queue works this way. So here is the front of the queue and here is the rear of the queue. So queue is pretty much like our queue in a regular paradigm, right? If you go to movie theater in the olden days, of course these days everybody is booking online, but in olden days, in my childhood and my college days, I used to stand in the queue for more than an hour to get the tickets. So it's pretty much like that. It's a ticketing line for theater or for railway ticket. So these are pretty common experiences, I think, in our life. Satish Gar, I think the same experience for you, I hope.
Yeah.
That's
stand in lamp queues.
Exactly, yeah. So that's the queue. Basically, queue is, you can think of as the front of the queue where the people are giving a tickets or like validating their tickets. Let's say front of the queue, they validated their tickets and they entered into the theater. And the rear, let's say rear is something like they will get a badge or they will get an identification. Okay, you are eligible. Let's go here. Okay. So insertion happen at the end. So insertion and deletion happens on different ends. That's the main part. That's the main difference between queues and stacks. Stacks both happens at the same end. Insertions and also removal happens at the same end. But in case of queue, insertion happens at the rear and the removal from happens at the front. Right. Once your ticket is validated at the end, once you are qualified, you will just go inside. You don't be in the queue anymore. Once you have the ticket, you will be free. So similarly, how can we achieve this data structure using stacks? So using linked list. So what are the main operations? Here is the main operations, right? NQ adds an element to the queue. Basically, NQ is, it will add an element, and DQ, which removes an item from the queue. The item are popped in the same order in which they were pushed. If the queue is empty, then it's said to be under flow condition. Basically, if the queue is empty, you cannot even remove anything, right? And there are two, I think, the front, get the front item from the queue, and rear, get the rear item from the queue. So I think these are all additional functions or additional methods. These are the main methods: NQ, DQ, and front and rear. Probably size is also another thing we can also have it. But here is the front and rear. Will tell you who is the front element and who is the rear element, who is the front person, and also who is the rear person. So those are the things. So how can we do this in a linked list? So let's go back to our whiteboard. Here is the whiteboard I can use. Okay, let me get my pen here. Here is the pen. So yeah, this is my own app. I don't know. So I think I told many times before. So this is basically Inking Alphabets is app I created around 6 years ago, 2016, I guess. Yeah, 2016 I created. It is available in the store. If you have Windows laptop, Windows PC, touch screen, it's touch screen enabled. Very useful app for learning alphabets for kids. Basically, I created when my kid is at around 3 years or so. 3-4 years. So she's learning all this, it's like you can add your own language, Chinese, Spanish, Tamil, or anything, and then you can practice. That's practice. And as well as it has an inking slate where you can annotate, you can write anything. That's what we are going to use. So here is the app. So sometimes I use this. So inking slate and inking this is inking boards. So this is a very very easy to write, and you can also save it. It provides a saving as a picture, and we can also load a picture on top of it. We can annotate. So let me try to use this for explanation. Okay, so we all know linked list has two things, right? So Satish Gar, just to remind that linked list has two main constructs. In every node, linked list has a list of nodes, right? So every node has a data. Here is data, and this is the next pointer. This points to either next element or either null. Null means like it won't point to any other element in the memory, right? So the main difference between arrays and linked list is basically arrays are contiguous, like they are continuously allocated. Like if you create an array, in our program, right? All these elements are created in the same order in the array, in the memory. This is memory. This is hard disk or the RAM. This is RAM, right? So they will be in the same order with the same memory. If it is at the 1111 and the second element at 1112, I'm just giving an example. So this is the allocation of array. But in case of linked list, the one element can be here, the other element can be somewhere in the memory. It could be at 1156 and it could be as 2212, something like that. So it's completely allocated at a different random memory by the processor. Okay, only way to get to the next element is address here. What is the address of this one? This address will have 12212, the address of this element. This is the address, right? So this 2212 is the address of the second element that will be stored in the next variable. So is it clear, Satish Garu?
Yeah, yes.
This is the main difference between arrays and linked list, right? So these memory objects, the linked list always have a pointer called head. This head will tell you what is the first element. If I know the first element, I can get to the next element, right? If this is the first element, let's say this is the first element, this is the head. So once head value is 1156. First I have to go to 1156, this element, and then from here I can go to any element. It's a kind of chain process, right? First you know the first one will tell you what is the next element, and the second one will tell you what is the second element. So it will go like that. So the iteration, basically, if you want to iterate with the list of elements, you need to extract the next value and go to the next element. So this is called node, and linked list having a head is just a linked list. So once you have the pointer to the head, that's it. That will navigate the entire list. So the main problem here is arrays will give you length. Simply what is the length or size, it will give you how many elements. But in case of linked list, we don't know, right? We need to navigate and count. That is another difference. We usually don't maintain the count. So sometimes we will maintain. If we are creating a stack or our queue, we can maintain the count. As you are removing and deleting, we can maintain the count of the elements. So the other thing is what I'm saying is, yeah. So the other thing, insertion and deletion. So what is the main drawback with the array? The drawback with the array is you cannot insert element in the middle, right? If you want to insert element in the middle, you need to shuffle all these values in the memory. So that is really complex process to do, right? So how can we do that? We need to allocate another memory. We need to swap all these elements, right? So, but how can we do in terms of linked list? Satish Gar, can you tell me how easy to insert an element in a linked list? Let's say you want, this is element A, this is element B. I want to insert here A2. How can we do that?
Yeah, we need to navigate until A2.
Mm-hmm.
Now point the next pointer to A2, and from the A2 point to the third one. We can
Exactly. Simply what we can do is we need to go back to the previous element all the way from starting from head, go to the previous element. Let's say A is a previous element. Now we just change the address of this one to here, and the address, whatever the address here, we can store here so that it will point to the third element. Yes, that's what we need. So that's very easy, right? Basically, we are not shuffling any elements. After this, there could be 500 elements, 1000 elements. We don't care. So we will navigate only until the element we want, wherever you want to insert. Let's say you want to, like we have 1000 elements, but you want to insert at the 10th place. You just navigate 9 elements, right? And just put the 10th element at the 10th place. And from here, 11 to 1000, 1000 or million, we don't care. So we don't need to shuffle any memory. It's efficient to insert an element. That is the main advantage of linked list. And it's a dynamic, so there is no fixed size, right? So in terms of array, you need to define, hey, we need 1000 or 100. While writing the problem itself, you need to decide what is the size of the array you want to take. But in case of linked list, it's endless. It's an endless kind of thing. You can have n number of elements. That's the main. So whenever we are talking about linked list and interview, better to have all these in mind so that we can answer those questions anytime. So why are you taking a linked list? What is the advantage? All those things. Okay. So now let's go back to our main problem here. How can we do the queues? So here is the linked lists. I'm just adding few elements here. So now let's say this is a queue. Let's say these are in a queue. So this points to here, this points to here, this points to here. And as we discussed, this is the front of the queue, and here is the rear of the queue. So whenever I say insert an element, let's say here we have B, C, D, E. Okay. So now we say insert D in queue. If I say NQ, this NQ, please NQ A. Okay. What we need to do? So we need to, let's say, they don't say any node. They will say just NQA. I want to element NQA. So with the data A. So what we need to do is basically we need to create a node and we need to put the value A here. And what we need to do is, what is the address? This until now the rear points to this B. If you say, hey, who is at the rear, right? It will say R will tell you that. So let me double check. That's the same thing, right? Rear is here, front is here, and we are enqueuing at the rear. So now we are saying, so rear will say like 1111. This is the address of the rear element, this element B. Okay. Now what we need to do is we need to create the new element A and put this address 1111 here, so that A connects to B and R simply points to A. Correct? That is what basically the enqueue process. So whatever the address in the R, we are putting that address into here 1111. Now we already created A created somewhere in the memory. A created at 7786. Let's say that 7786 will store in the R. Now if anybody asks, hey, who is the rear element? It is 7786. What is 7786? That is A. Correct? So last time, Karanya, I don't know whether you remember, last time we discussed about we can create a queue using double linked list, but that was a mistake. I think we no need any double linked list to create a queue, because this is a queue. Queue only requires access to front and access to rear. We never navigate a reverse, right? Because we always remember, if you remove this element, okay, we'll get the next the before element. If we remove E, we'll get the D. Correct? So we don't need to navigate. We don't need to navigate in a reverse way. If any possibility, if any requirement to navigate in a reverse way, that is the only situation we need double linked list. DDL, double DLL. Double linked list is another data structure where it will allow you to navigate back and forth. But here you can navigate only in one direction, right? The single linked list is always like one direction, right? So this is NQ operation. NQ operation you understood, right? Creating an element and store the rear address here, and then change the address of the rear to point to the new element. So is it clear to both of you, Karanya and Sadish garu?
Yes.
Yes.
Yeah. So that's the NQ operation. Now let's talk about DQ. So how can we do the DQ? So similar here, we need DQ is basically we need to remove. So we already know, hey, who is the element at the front? It will say 7712. Let's say that's in it. That's what front element. That is what E. This is 7712. What we will say is, okay, what is the value of out of it? The value is E. And now what we need to do is here is the front element, right? Let me see how to, I forgot. So yeah, sorry. I think we are not removing, right? So yeah, here is NQ. NQ happens here. DQ happens at here. I keep forgetting how to do this. DQ. What we need to update is
Friend should point to the D.
yeah. Linked list. Yeah, here is the Q, right? Here is the code. We can see the code to understand how to do this. I will show it again. So if the front is null, return it. Otherwise, front dot next. Temp equal to front, then front equal to front dot next. Store the previous front and move front to one node ahead. Okay, so we enqueued 10 and we enqueued 20. Okay, let's iterate through this. Okay, maybe that's the easy way to understand. So I keep forgetting, how to do this. So there is a little tricky thing here. I'm going to do this. Okay, so what we did is we enqueued 10 here. So 10 is here, and both the front here is the rear and here is the front. Front points to the same element. Now we enqueued 20. Okay, now the rear points to 20, right? And front
points
sorry,
to 10.
Yeah, front points to 10. So now what we did is we DQ'd one element. We DQ'd this. So now front points to nothing basically because there is no next element for front, but rear points to 20. Okay. Now we DQ again on the line number 82. We DQ again. So that means let me see how it is working. You cannot even go to the next element in the front, right? The front is null. Okay. DQ.
So when you DQ, like the first element will be the rear and first, right?
Oh yeah. That's right. You are absolutely correct. So when we enqueue, what are we doing here is when we enqueue, we are creating a node and we are inserting at the rear, right? If the rear is null, we are inserting both the front and rear to the temporary element return. Otherwise, we are inserting at the rear. Okay.
Rear.
So now I'm trying to understand here. So if you DQ 2 times, right? So once you DQ first time, okay,
10 goes away.
Yeah, 10 goes away. But here it says 10 like front equal to front dot next. This is what I'm trying to understand. So this dot front is basically F here as front. Front equal to front dot next, which is null. Front dot next is null. There is no front here.
Yeah.
Okay? So now if the front is null, next time you cannot even DQ. You cannot even DQ, but we need to DQ 20. So I think it's I'm still confusing.
And
I don't know whether
this line number 67 also confusing. So in earlier statement, you are setting that front to null.
Yeah.
And now this is null. So rear is also null.
Exactly. So let's see if
So
I DQ.
the first object. The first
Got
element
it.
itself like goes.
Yeah. So let's see what is the linked lists insertion. Okay, null object reference. That's what is happening here. So
Because you don't have anything. So
we don't have anything. Yeah, we DQ 2 times. Let's. I think there is still a problem in this algorithm. I guess I took from the GitHub's like a Geek for Geeks. So now let's see. So we inserted 10. We inserted 20, and that is the front is 10 and rear is 20. Now we DQ'd one time. Okay, we DQ'd one time 10 removed, and we enqueued 30, 40, 50, 60. Okay, let me do this in a diagram. Looks like there is a bug in the problem. We need to look at that.
yeah, yeah,
We'll see. So first we inserted 10, and then both rear and this is front, and this is I'm sorry, this is rear and this is front. So now we inserted 20. This is 20. Now this becomes rear and this becomes front. Okay. And now we DQ'd one element. We DQ'd 10. So that means front is right now it pointed to null. At this point right now, because you cannot point back. I think definitely we need double linked list. I guess I'm still confusing. Some guy written like with single linked list. Now front is null. Now we DQ'd 30. We enqueued 30. Okay, 30 is here. Points to 20. Now it is rear. And we enqueued 40. Sorry. We need to have something like this. So if we enqueued
Suresh,
40, 50, 60. So it will be like this 60, 60, 50. Yeah, go ahead. Go ahead.
okay. Before constructing the linked list, why don't we just write down a simple queue of 1, 2, 3, 4, 5, and how it is inserted and how it is deleted?
You mean like a
A
normal queue,
simple
like you
queue,
want
yeah,
to
yeah,
use?
yeah, simple queue. I think the direction is wrong in this problem we are discussing. 60 is
Exactly. That's
pointing
what
to
I mean.
50, 50 is pointing to 40, where it is not. Won't be. I think so. So let us
Yeah, so
construct a
because
simple
I'm
queue.
enqueuing in that order, right? I'm
Yeah.
enqueuing 30. See, I'm enqueuing 30, and after that, I'm enqueuing 40. So 30 is in the line, and 40 came into the line, and then 50 came into the line, and 60 came into the line, right? And here is
yeah.
the rear. Rear of the queue is 60 right now, and front is basically before 20, there is a 10, but since 10 is removed, front is empty. Front is empty right now. So if I DQ again, now it says front is 30. So which is right, because if I remove 20, right, this is front. So this is front. It is still working. I'm still trying to understand how it is working. So which is right. If you remove at this point, if you remove the 20, right? So
Yeah.
30 is the front. So front Q front is 30, rear is correct here. So let me see. Yeah, there is a yeah, here is NQ. If rear is null, we are adding those. And if with the okay, wait. So
The
if the
here the
front is
next.
null, rear equal to null. Okay. If this
No, no, the program is correct because like, the next is the address part of the node, right?
yeah.
So that's right. That's not null.
So well, my question is this is where I stuck here. So let me do this. So if I remove 10, right? If I remove 10,
Yeah.
what is the next value of 10? That is what they are doing here, right?
So
So
next value of 10 is always null.
null, right?
And yeah, so then the next in line is 20, right? 20's next value is null because front nobody is there, right? This is queue.
Mm-hmm.
When nobody is there, that's the end of your queue. It's null.
Yeah.
It's pointing to nothing.
Oh, rare
That's
also
the
null. We are making rare also null in the situation.
Yeah, front, when front is pointing to nothing.
Yeah. This dot front dot next. This dot front equal to front. Okay. If the front becomes null, then change the rear also null. Okay.
Yeah.
So after having 10 and 20, after removing one element, both will become null, right?
So if I remove 10, okay, the front, now I'm pointing the front to rear.
Mm-hmm. So now 20, when you are inserting at the 30, let's say when you are inserting at the 30, what happens is both is null. Both front and rear is empty. Okay. Now I got it. Now, this is why it is working. This is why it is working. Let's see.
It's trying to add a new element always. Like,
Yeah. I think there is a small bug. I need to fix this. See 20 and 60. Oh, it's still there. Okay. So here is how it works, right? So if we are here, we can see on the diagram as well. So so if we are removing front element, right? If we are removing front element, the front needs to point to the second element.
yeah,
That is what I'm trying to understand how it is pointing, because if you go to the next element, right?
yeah,
But you're not going further. You have to go back. If I understand correctly, how can we go back without having double linked list? So that's the main part I was confusing here. Okay.
yeah. You need to have a point to the back one.
The previous element, basically.
Yeah,
Previous element, which is
we
which
don't
is
have.
not possible. Which is not possible in this solution, which is not possible. I don't know how this guy implemented. So implementation of queue, we need to keep track of two indices, front and rear. We enqueue an item at the rear and dequeue an item from the front. If we simply implement front and rear indices, then there may be a problem. The front may reach the end of the array. The solution to this problem is to increase front and rear in circular manner. Hmm. Oh, it's a front and rear in a circular manner. He's saying in a circular manner. Oh, this is an array. But I think anyway. So I think this requires a little more in-depth, understanding how this is working, or if any bug is here, we need to look at it. Okay. So see, this is the one. Store the previous front and move front one node ahead. Store the previous front. Right. Dot front.
And he's not using the temp anywhere.
Yeah, that's the thing.
That's the first thing I observed. Like,
Store the previous front. Okay. Interesting. So
Suresh,
yeah.
I just shared a link in Discord. Just look at it. I
Sure.
think you are, yeah.
Do you implement queue implementation in Java using linked list? Very nice. That's good. This may be a good one. Okay. Okay. Rear front element removed from the front is here. Rear is here. Oh, element added to this end. Oh, okay.
okay. Actually, like we interpret it in the opposite way. Actually,
Opposite way. Yeah.
so
I think that's
we need to save store in the same location, but when we have to delete, we have to delete from the front. When you have to
that.
add from the back, then this algorithm works. Yeah, that's
Yeah.
only thing is we have interpreted in a opposite way. Like,
Yeah, I think the diagram is not the correct one. I think this
yeah,
is different. Okay. So, okay, this is good one. Yeah, thank you for sharing this. So basically what we doing here is front, we are elements removed from the front. So if you remove one, it will go to the next one, right?
yeah,
That's what we are doing exactly. Like that. That's good. Thank you for sharing this. So if I go to the problem again, so let's in DQ, let's go to the DQ. If the front is null, there is no more elements. There is no one in the queue. We are
yes,
returning.
yes,
Otherwise, we are going to the next element. we are going to the next element. So whoever is the, and that's the next friend.
Yeah.
Okay. So, and then front is null, rear is also null. That means if by any chance there is no more elements, we need to
You
update
reach.
the
Yeah, you reached the end of the queue.
end of the queue. Yeah, basically complete all the elements are completed. All the people are processed in the queue. That means we need to change the rear also. Do that. So now if I go back um, here, right? So now if we need to insert, so rear need to insert. So rear element is here. So we can just create a new element and insert there, like 1, 2, 3, 4, and the next element, right?
Yes.
So that's what we are doing. Basically, here is enqueue. We created a new node, and if the rear is empty means both front and rear are like there is no elements as of now. So we are putting both front and rear equal to temporary element, because both front and rear points to the same temporary element which is created, and we are returning. Otherwise, we are just adding at the rear,
Yes.
and we are updating the rear. At this point, we are not updating the front. That's right.
Yeah.
Okay, I think I did a mistake for understanding here. So basically,
Yeah, our diagram is done. That's it. Yes.
our diagram is wrong. Where is my pen here? So, wait, sorry, I'm trying to find my pen here. Yeah, here. So basically, this is front and this is rear, right?
Yeah,
If
then
you are,
it's right. Yeah, yeah.
yeah, from the front. Okay, so we are basically, let's say here is the counter. Here is a ticket counter. Okay.
Yes.
Now the people are coming like this.
Yes.
People are coming like this, but the link is like this. Link is
Yeah,
like
link
this.
is in the
The
opposite
link,
direction here.
exactly. That's where I was confused. The line formed from here. Line started here, like kind of the rear of the line here and front of the line here. Here is a ticket counter. Okay.
Yes.
Now, but the next element. So this guy ticket was validated. We will remove this. Now here is the front. The front points to 50. Now this guy ticket is also validated. Now we will front points to the 40. Right. In the meantime, somebody came, like 80 came. 80 is another guy who came it. Okay, we'll say, okay, come here and just point here. Like whoever is the element here points to this 80,
Yeah.
and
80
rear
becomes
points. Exactly. It's not like the other way. So the direction, basically the links go in this direction, but the queue is like this. Queue is operating like this. That was the misconception I assume. Now we are clear, right?
Yes, yes, perfect.
Okay. Sorry
Yes.
for that confusion. So Karin, are you clear now? Thank you for sharing the nice
Yeah,
link.
yeah,
Actually,
yeah.
it's really nice. This is what we need to look at. I think very nice. So yeah, it's exactly the same implementation. I hope, right? It's exact same implementation. Yeah,
Yes.
cool. I think we are good on this one. So we can. So that's what we are doing here. Now let me iterate last time. One more time. Let me iterate with the new diagram, just for my understanding. So if I iterate the exact same input here, let's iterate. So we got this is a front, and this is rear. So we inserted 10. So when we insert 10 will be here 10. So now both point to 10. Now when we include 20, right? 20 is here, 10 points to 20, and rear is 20. Front is 10, right? So front is 10. And now we say who is the front? 10 is the front, 20 is the rear. That's what we just printed here, right? So here is a counter. Let's say this is the counter, ticket counter. So who is at the front? 10 is at the front, and who is at the rear? 20. So now we dequeue. So 10 will be removed. Both front and rear points to 20, right? Now we added 30. We added 40. We added 50. We added 60. So all these points to like this. So rear finally points to 60. That's what rear point to 60. Front is still pointed to 20, because front is still there, 20 as it is. Correct? Now it's perfectly clear. Now if I remove this here, this will remove 20 and the front points to 30. That's what is happening here. I added another DQ. It is going to touch 30, grade points to 60.
Yes.
Awesome. Thank you, both of you, for correcting me. This is where we need. That's why it's kind of all kind of learning together. Okay.
Yeah.
Thank you for that. Awesome. So, shall we jump into the next problem, or is it okay? It's already night, I guess, but okay. This is also simple, small one actually. The cloning, create a copy of the linked list. Shall I go ahead?
Yeah.
Yeah.
Awesome. This is also a curious problem. We are basically cloning. What is meant by cloning is basically immutable list in Java. So immutable list means read only. Let's say you have a list. Okay. Somebody will ask you a linked list. You need to create one more. It's a read only wrapper or a collection. They do not support any modifications or removal. So basically, what we can do is this is the simplest way to say. We have a linked list. Okay. So we have this linked list. So now we want to create, let's say we have one here, two here, three here, four here. We want to create exact same replica of the same nodes, okay, in a different place in the memory. That means we just need one, two, three, four. That means we are cloning, basically cloning in the sense copy, right? Complete copy, cloning of a person, cloning of an animal. So where they look like exactly same, but they are not same. So here these two lists are exactly same. 1 points to 2, 2 points to 3, 3 points to 4. But these are two different, like it's four elements here, these four elements here. There are 8 memory locations in the memory, like 1, 2, 3, 4, and another 1, 2, 3, 4. These 4 points to this, and these 4 created after our program, that will mean that though they will be in a different location in the memory. That means basically we need to create a copy of each element, and we need to link in the same order. So cloning. So this 1 points to 1 here. Similarly, this one points to this 2 here. 1 to 2, 3, 2 to 3, 3 to 4, right? So if you want more explanation here, let's say this is 1112, this is 1115 address, and this is 1178 or 78. Now, what is the address here? The address here is 1115, right? That way you can go to the next address. But here, when you create the clone, let's say this was at 887. This one created at 887, and this one created at 919. This address, right? It looks like exact same element. You should not have 1115. If you have 1115, it will go to this element. We want to have the copy of this element. What is the copy of this element? This one. And what is the address of this element? 919. This is number 2. So here we need to put 919. Similarly, what is the address we need to put here? We should not put 1178. We need to put the copy of this 1178. What is the copy? Here is the copy. What is the address? Let's say 187. We need to put that 187 here. So that is the main intention here. So we need to create the copy of each node. These are the clones. So this is the clone of this node, and this is the clone of this node. This is the clone of this node, and here is the clone of this node. Now the address changing is really important. When you create a clone, we will create a clone of data. We don't want to take the same address here. If you're taking the same address, this node will point to this node in the memory, correct? That's what we need to avoid. So how can we create a separate linked list of the original linked list without touching or without changing? There are two questions actually. You can change it, you cannot change it, but let's make it simple. You should not change the original linked list. You just need to create a clone of linked list in a separate place in the memory. That's the clone. Is the problem clear?
Yes.
Yes.
Yeah. So how can we do this? So the problem given with the linked list, which is a head points to the first element. So how can we do this? Any idea?
loop each element and copy the data,
Mm-hmm.
and then point and you will have h1 for that thing, and here also you need to have h1 and t1. Every time you
Mm-hmm.
copy, you change h1 to the new node and tail to that one, and you need to add a tail at the end of the next element. And
Exactly,
then
exactly.
that way you are just increment, you're always changing the tail.
Yes. So when we are looping, right? Let's say we, as you said, let's say we created a counter or something. There is a, it's not counter. Let's say, yeah, current node points to this node. Okay. Now you create a clone. That's nice. Very nice.
Yes.
Now current points to second node number 2 here.
Yeah.
Okay. Now you created a clone here. At that point, the problem here is at that point it created 919. You know the address, the current point. So the C1, C2, let's say C1 points to the current node, number 2 here. C2 points to the clone of the current node. Let's say this is the 2, right? But the problem here is when you are at this location, you need to update this one. You need to update the address of previous node. Correct. You need to update this one. You already let's say c1 and c2 already you created these two nodes. Now you navigated c1 points to number 2 in this second in the main list, and c2 you just created new node at 919. At that point how can you update the 91, how can you update the address of the previous node?
uh,
That is problem
Cloning
here.
is like here actually, like we are completely creating a new node, right? Then new node dot data is equal to from old node dot data, and next pointer is pointing to the t1, right? We're not
Yeah,
cloning
yeah. So
directly this one. Yeah,
yeah, when
we're
you're
copying each and every point, right? Data part as well as the address part.
That's good. That's good. If you are copying entire thing, let's say if you are copying the whole thing as is here, let me select a different color. So if you copy the entire thing, you will copy the data. That means one will be here. And if you copy the address as well, as I said, it will tell you 1115. Go to
Yeah,
1115. That is the problem, right? It will connect to
yeah,
this
yeah.
node. So it has to connect to the node you create afterwards.
Yes,
So
then yeah, it has to point to the tail, which is null here in this point. First loop, first
exactly.
iteration.
Either you can put null. You can put null, no problem. You don't copy the address. So one created the clone of first node created with the next address null. Now you go back to here. This is C1 and this is C2. You created a clone of C1. We created number 2 here, and you put null here. At that point, before you proceeding, you need to go back and update the address. Otherwise, these two never link. Correct. In order to link this, in order to link the cloned one to the cloned two, you need to update the address here. Correct. That is the crux of this problem. Are you following, Satish and Karanya?
Yes, yes,
Yes.
So if you go with the normal iteration, normal loop or kind of navigation, only thing is when you after you create the new node, you need to find the address of the new node and go back and change the address of the newly created previous node. That is the problem. You cannot go back because if you are having two pointers, maybe if you can create another, maybe I'm thinking like maybe if you maintain C3, maybe you can do it. But there is a simple solution I found, which is like let's use any existing data structures. Let's assume that you can use the best data structure is hash table. I don't know whether you know that hash table has key value pairs, right?
yes, yes.
So we can use the hash table to achieve that. Okay. So how the hash table help us is like this. So what I'm doing is okay. So what I'm doing is basically in the hash table. What I'm doing is in the hash table we will put the each value. We'll put the each node. Okay. Hash table has a key value pairs, right?
Yeah,
So we will create new nodes. we'll create new nodes and we'll put the old node here, old node and new node. Okay. So let me look at one more time to double check algorithm. So yeah, that is what I'm doing here. Yeah, we are putting the whole node into the data structure. So yeah, here is a clone. We are adding a node and we are adding to the h dot data t equal to new node. Okay. So we are adding just a minute. Yeah. What I'm doing is what are we doing here is, so one created, one already have. We will add the second one here. The basically the cloned node. You created original node. We are putting in the hash table, and this node points not a point. Basically, this is the key. This is the key, and this is the value, right? There is no
Yeah.
point or anything. If you go to this node, it will tell you, hey, here is the clone of my node. Okay, we are creating new. We are creating a second clone node, and we are putting this is the clone. Let me put in a different color. This is a clone of two. This is one. This is two. So similarly, we'll put the original node here, and we also put the clone node here. This is the three. So basically we are using hash table to find the clone node. Okay, let's see how it helps. So what are we doing is we are navigating to the original list, and we will create new nodes, and we will put the old node as a key and new node as a value. Okay, now what are we doing here is, when the second time we will navigate, we need to just link it, right? We created these new nodes. This diagram became really bad. Let me, yeah, maybe I can clean again. So let's say we have these nodes. Now I created, as I said, while I'm creating, I'm also building a hash table. Okay, this is the node. This is 1 here, 2 here, 3 here, 4, and here is the 1. I'm putting 1 while I'm creating 2. While I'm creating the cloned node, right? Here is a clone. I'm putting the clone node here, 1. Okay. When I'm creating 2, when I'm navigating to the 2, I'm putting the clone node 2 here. So these are not linked yet. I'm just navigating to each node. I'm building the hash table. So 3 is here, and I'm creating the clone node, and I'm putting that clone node in the hash table. And again, go to the fourth one, created 4 here, and created a clone node in the hash table 4 here. Okay. Now we created these 4 nodes, 1, 2, 3, 4. Now we need to link them. So it's a 2 iteration process. How can we link them? Let's go to this. Let's go to this the main linked list, and what is the, so we need to put the address here, right? So what we need to put the address here is, we need to go to the next element here, and we need to find this element. So basically current dot next, the value of the, this is a key and this is value. So h of current dot next. So current dot next is 2. So that's the address of the 2. Right? So that will give you number 2 here. So 1 will be pointed to here. So let me show you this here. Let me show you the algorithm here. Okay. Here is the node here, and here is the node data and add links. This is a pretty common data structure node here, and here is the main problem, and here is the cloning. How can we do? So without changing the original node, but you can use extra space. So here is the head node, and as I said, we are taking a dictionary. Dictionary is hash table. Dictionary is in C#. We call dictionary, which has node and node, and what are we doing here is, we are navigating through this while loop, T is pointed to head right now until T equal to null, until T not equal to null. So once we are creating a new node for T dot data, this is a new node. As I said, we are putting into hash table with old node T and N. T is the original node, N is the new node, right? N is the new node we just created with the T dot data. If the T is pointed to 1, we'll create 1. If T is 2, we'll create 2. So we are putting in the hash table. Okay. If head 2 is null, we are putting head 2 equal to N. That means if the head 2 is the new linked list, so then we are doing this. Okay. So here is the T equal to T dot next. We will navigate to the next element. We'll create the clone of the element and we are putting in hash table. Okay. So we'll complete this. Once this loop is completed, we have hash table with all the old nodes and new nodes. Now T equal to head 2. Now we are using T variable to navigate the head 2 and P equal to head. We reverted like another, we just create, we took another pointer which points to head. Now P not equal to null. Now what are we doing here? If P dot next not equal to null, P dot next means P is basically this one. P. We are using P again, navigate to each element. If P dot next not equal to null, okay, then T dot next equal to H of P dot next. That's what I just said here. So T dot next, T is here. T is pointed to here. So T dot next equal to H of P dot next. So P dot next is here, right? So H of P dot next is 2. We will get this value. These are all just addresses, right? So 2.2, if I give you the original 2, you will get the cloned 2, cloned value of 2. If I give the original 3, you will get the clone value of 3. That's what we are doing. H is like basically the hash table of P dot next. Hash table of P dot next equal to T dot next. So T dot next equal to hash table of P dot next. So basically we are updating this by using the next value of this and then hash table of that one. This is a main important line in this whole algorithm. So that's how we are updating. If P dot next is null, we are simply putting P dot equal to null. Basically, at the end of the node, P dot next is null. We are putting this one is also null. So if this is just last element condition. And then we are moving both at the same time. P equal to P dot next, T equal to T dot next. So basically, P points to the next element and T points to the next element. So in order to update the next pointer here, we are using P dot next and its value in the hash table. Is it clear?
Yes, it's clear.
Yes.
It looks like little complicated, but if you follow this algorithm, if you follow this very quietly, you can easily understand. There are two loops. One is building the hash table. Basically, we are creating clone here and putting in hash table. That is one process. And the second process is basically chaining. This is the chaining of the second linked list. For the first process, we don't create any links. In the second loop, we'll create these links by using the clone of this one, by using the original value and go to the next one and the clone of that next element. So this is the main line to understand. Like line number 88 is the primary thing to understand. Okay, so these are the two problems I practiced, and we can have other things, double linked list, and there are other things we can discuss in the next classes. Or I'm also thinking to go to the trees very soon. Trees, we have a couple of problems in trees. I practiced binary tree, and like different searching algorithms. There will be a lot. So yeah, how is the session so far? Any questions?
It's good. No questions. Like, yeah.
Yeah. So Satish, is it helpful, you think, or any improvements or any kind of feedback?
It's helpful. Yeah, because like it's been like 11 years that I haven't attended any interview yet. So that's the reason I wanted to connect to this and brush up things.
Yeah, that's right. I'm just moving to different room here. Yeah, it will be helpful like when we are practicing more, and if you are attending interviews, right? It's not only attending interviews, just learning these concepts is always helpful, correct?
Yeah, it's always helpful.
Yeah, so that's the main intention. So how is it, Karunya? Is it good, or any questions from your side?
No, Suresh. I was confused about the copy of immutable list. That's the only thing I had. Now I'm clear about it.
So you got the clear
Yeah.
understanding, right? What is this
Yeah.
copy? I don't know whether this is a kind of entry question, but this is interesting question I practiced in one of the books. So there is a slightly complex part of it as well. So it, like, maybe if you're interested, we can practice. But there is a complex part is something like this. The list is like this. Okay.
Okay.
So every list has two elements, like two addresses. Like there are one is next element, next address, and next to
Mm.
another one is rand. There is a rand address, random address. Basically, next is always points to next element.
Okay.
Rand points to any random element. It could be third element, it could be 10th element, it could be thousandth element. So there is only two, and of course there are no two. There are no two. Only two addresses. One is next. This is next, and here is random. Okay. So
Okay.
the node is like this, right? This is the data, and this is random,
Okay. The
and
next
here
one.
is the next element. Next, there are three different attributes in every node. How can we clone that? That's really complex part, right? So here we have node has only data and next.
Mm.
If you also have a random address, and that random address could be anything. It could be, like, as I said, 10th element, 20th element. This random can go to any different element. Let's say this will be 100th element. This can, the rand address of this one can go to the another element in the list. So how can we do that? So how can we clone this whole thing? That's another interesting part. So, but anyway, so these are the problems I saw somewhere in another books, but I don't know whether these are really interesting in terms of interview. But it's a curious question, right? It's interesting question in terms of learning.
Yeah, it is.
Yeah, cool. Great. I will share the code of these two algorithms and all these links, and if you do, we can definitely look back and refer anytime. Okay.
Okay. Thank you.
Awesome. Okay. It's already been like 10:30 there. Thank you, Satish Garu, for joining, and thank you, Karanya. I hope it is helpful.
Thank
So
you
we'll,
for the
yeah,
sessions. Yeah.
we can meet again next week. Okay.
Yeah.
Sure, sure. I have created this Discord account. I have sent you the email.
Oh, nice. You already created. Awesome. Awesome.
Yeah,
That's really good. I can just, if you go to Discord, like there will be a Discord ID or something. It will create an ID. So yeah, let's connect there. I will see if I can add to one of these closed groups. Okay. Yeah. Sure, Sadish. Yeah. Thank you, Abni.
yeah. Discord ID is 8042.
804. Okay, okay, okay. I will try to connect there. Yeah, no problem. Awesome. Thank you, everyone. I think then we can end the session, and we can meet next week. Okay.
Okay.
Have a
Okay.
nice
Sure, sure.
week ahead. Yeah.
Thank you. Thank you.
Thank you, thank you.
Awesome. Thank you. Bye.
Bye, bye, Suresh.
Bye.